An ideal gas was expanded from the initial state to the volume V without any heat exchange with the surrounding bodies. Will the final gas pressure be the same in the case of a fast, and in the case of B, a very slow expansion process? Solution. During very slow process, that is isothermal process, the change in temperature is zero, as a result of which the change in internal energy is also zero. From the first law of thermodynamics, dq equals to d plus dw. This implies 0 equals to 0 plus dw, since dq equals to 0 from question and d equals to 0 for isothermal process. This implies dw equals to 0. The work done can be calculated for isothermal process. dw equals to P1 V1 log P2 by V1 equals to P1 V1 log P1 by P2. Now P1 V1 log P1 by P2 equals to 0. This implies log P1 by P2 equals to log 1. That is P1 by P2 equals to 1. This implies P1 equals to P2, which indicates that pressure remains same. Similarly, for adiabatic very fast process, dq equals to 0. In this case, dw equals to minus dE, and hence can we prove that the pressure will be more after the adiabatic expansion. A thermally insulated vessel is partitioned into two parts so that the volume of one part is n equals to 2.0 times greater than that of the other. The smaller part contains nu1 equals to 0.3 moles of nitrogen and the greater one nu2 equals to 0.70 mole of oxygen. The temperature of the gases is the same. A hole is punctured in the partition and the gases are mixed. Find the corresponding increment of the system's entropy, assuming the gases to be ideal. So the insulated vessel is partitioned in such a way that V2 by V1 equals to n. That is, the volume of one part is n equals to 2 times greater than the other. When the hole is punctured in the partition, the gas in one part will goes into the other and vice versa. That is, the mixing of gas occurs till the pressure equalizes. Now, when the first part gas goes into second part, only volume and pressure change because the temperature remains same given in the question. Hence, from first law of thermodynamics, dq equals to d plus dw equals to 0 plus p dv. Hence, dq1 equals to nu1 rt dv by v equals, this implies delta s1 equals to integration dq1 by t equals to nu1 into r into integration v1 to v1 plus v2 dv by v equals to nu1 r log v1 plus n v1 by v1 equals to nu1 r log 1 plus n. Now, when the gas of the second part goes into the first part, du equals to 0 because of the same temperature. Hence, dq2 equals to dw equals to p dv equals to nu rt into dv by v, and delta s2 equals to integration dq2 by t equals to nu2 into r into integration v2 to v1 plus v2 dv by v and nu2 r log 1 plus 1 by n. And total entropy increment delta s equals to del s1 plus del s2. Hence delta s equals to nu1 r log 1 plus n plus nu2 r log 1 plus 1 by n. Answer. Using now putting all values of R equals to 8.31 joule per Kelvin per mole and nu equals to 0.30 and 2 equals to 0.70 mole, n equals to 2, we get delta S equals to 5.0 joule per Kelvin